don't know any good example for glycerol. I'm not doing manufacturing foods too much, but I tell you one example. When we freezing bacteria culture, if we want to keep it alive, we can use it after we salt it. We usually keep the bacteria at minus 20 degrees Celsius with glycerol, which means a little bit like oil there, because glycerol is a cryoprotection agent. Okay, so that's an example. Otherwise, the lower temperature will also damage maybe the bacterial cells. So we add the glycerol there as a cryoprotectant. So just to give you an example. Okay, now here is something else we want to mention. Okay, ideally, we want to prevent the crystallization. We want to have the glass form. But it's not easy to do. Number one, glass forming is highly related to moisture amount of the food. Or moisture contents. This curve tells you, I'm not going to draw it or everything. Something like that. This is TG. This is the moisture content. Okay, and that is temperature. What that means, if the products have a very high moisture content, let's say somewhere there, you only need a very low temperature. It can be, let the products become glass form. But I tell you, at this moment, it's not good, because crystal, this is glass. At this moment, there is an intermediate status, which is called rubbery status. At this moment, the motility, the movement of the moisture inside of the structure of the food products is at a maximum status. That's not good, because the biochemical reaction, enzymatic reaction is at a higher level. So we have to avoid that. That is why, for those high moisture amount of water, if we want to let them to reach glass form, we need to do that. We need to add glycerol, especially the pure liquid products. Because if you only rely on the natural transform, at this moment, it is rubbery status. That's a highly biochemistry activity. Okay, so this is the first thing you need to know. Moisture amount of the foods will be impacted the glass forming. Number two, and I mentioned the small size of the molecular sugar. This figure tells you the molecular weight is highly impact the determination of the glass forming temperature, determination of TG. Why? Because polymers will have so-called thermal decomposition. Which means, if it's a polymer, we melted it. It's too large. It will so many different small molecules will come out. It is hard to determine its glass forming temperature. So the maximum we can get is starch. This figure tells you maltose, maltolysis, hexerosis until starch, it's okay to determine. But more than that, we can't do it. On one hand, we need a very high temperature. Another one, even we try to do experimental design, it's difficult to get it because those higher, huge polymers will be going through thermal decomposition. So you're not going to know which ingredients really pay much attention, play an important role in the glass form. Okay, so it's difficult to do. That is what we say the molecular weight determined by the glass transition temperature. And the polymers, because of thermal decomposition, so difficult to determine in labs, or we say in experiments. Okay. Third thing, it depends on different products. The glass transition temperature is highly related to water activity. That means available of the water, which means the vapor pressure of the water products should be divided by the vapor pressure of the pure water. Okay, so basically, this glass transition temperature decrease with increasing of water activity. So you can see that. Well, this is to understand water activity have a little bit of relationship with the moisture amount, at least correlated in most of the products. So that's easily understand. This is another study. We're not going to go very detailed, but I'll show you. This is another study showing you water amount, moisture amount, and the glass transition temperature is highly related to the amount of the molecular weight. The lower amount of the molecular weight, the lower the glass transition temperature. And you can see underneath, for each of these specific lines, the lower water content, the lower moisture amount, the higher glass transition temperature will reach. And usually at this area, that's not very good because we'll have a rubbery status happens. Therefore, we need to add so-called cryoprotectants. Okay, that's another example right. Okay, now we want to talk about water activity and the food storage. This is the one we already mentioned, and since Rebecca is not here on Tuesday, so I want to briefly to go over what we already talked about. On Tuesday, we talked about isothermal. This is what's going to be happening. This is moisture content. That is water activity. Okay? Now, the food products usually like that. And then we'll have another one like this. And we basically can have 3 sections. And this is, we call it absorption. And this is desorption. These are not really reversely linear. So we call it a hysteresis. Because which means it's lag behind. There is a 3 layer right here. This is monolayer. This is additional layer. This is capillary. Monolayer usually is bound water. So here, moisture amount is lower, water activity is lower. Additional layer in the mixture, a little bit loosely bound water, we say. And the capillary, free water, most of them. Or capillary layer water. Okay? Now, this is what we're going to be. Then we talk about the water activity. This slide gives you just a conclusion. Regarding the water activity, we are under the food storage. We care about three things. Number one is bacterial growth, including fungi, a microorganism growth, we will say. Number two, non-enzymatic browning, which means Maillard reaction. Number three, lipids oxidation. Those are the three things. What will cause rancidity? Three things for food products regarding storage. Okay, for me, I mainly care about this. We do lots of research for microbiology. Okay, here I give you just a conclusion. Once the water activity less than 0.9, almost no bacterial growth, but yeast and molds will grow. And 0.8 to 0.008 molds yeast will be inhibited. Less than 0.85, enzymatic is inactivity. However, lipids reaction could be very active, even it's very dry, even the water activity is very low. And this explains well for that. Okay? What is the lipids oxidation curve? This is lipids oxidation. Okay, what that means? Which means any of the food products which is low moisture, low water activity, let's say are chips, we care about lipids oxidation. Okay? Second curve, kind of like that. This is now enzymatic browning. Maillard reaction. We really care about is the food products right here. What's a good example? Condensed milk is a good example. Or raisin. But how about here? This area. We pretty much care about everything, but more important, bacterial growth. And the lipids oxidation also. And this figure will explain to you, during the food storage and the processing, based on the water activity and the moisture amount, we will very, very care about. Sorry, this is wrong. We will very care about, is there, this is what amount, water content. We will very care about that, which categories it fits, and what kind of the preservation we need to do to keep their longer shelf life. Okay, so that tells you about it. These slides, I think you have to do a little bit of switch. I don't think it's in the older textbooks, third version. I would recommend you to do a switch. Capillary water and the loosely bound water, just switch. I think the textbook is messed up. So just switch it. The reason is, if we go back to see here, if you read the textbook, it's a lots of mistakes there. Mislabel the figure, mislabel the table, and the redundancy, which means that paragraph, write it here, and write it again, coming from nowhere. It happens the whole textbook everywhere. Okay, because it's a difficult material. So you see monolayer, strongly bound, loosely bound, capillary, and free soluble water. So capillary water and loosely bound water is actually the same category. And actually the last section, kind of like capillary water. So this section, I would suggest you, I will take it out when I teach next year. These should be switched. Loosely bound water and the capillary water, just switch it. Okay, on the top, just switch it. So I will just skip this slide. Because more important is right here. It explains to you all these reactions. Okay, this is the one, which is a very good example of a Maillard reaction. So what happened for a Maillard reaction? Because of the lysine in the milk powder, so if you put a milk powder in the room temperature for a longer time, it will become yellow. Discoloration, that's not good. That's called Maillard reaction. It is highly related to the water activity. So you have the curve there. Look at the red dots. That means the loose free lysine, the amino acid is gone. And the blue dots indicates the yellow index, which means how yellow it is. So you will see when the water activity reach about the middle, which is about 0.68, that means the Maillard reaction is at its maximum level. So you have to avoid that range. Either higher than that or lower than that. If you do a storage, you must make sure you do a good packaging. That's important. The only thing what we can do is for good packaging to make sure the water activity is avoid this range. So here comes the question: water activity and the food packaging. Now why? This, we're gonna going back to this slides, how you explain it. Right here. Why we want to talk about these sorption isomers? Because every food product fits these three categories. This is A, hygroscopic. These type of products are very sensitive to the environmental moisture content. Their water activity are very highly related to its moisture content of the environment. A limited change of the moisture in the environment, they will change their products. For example, instant coffee powder. The second curve looks like that. That most of the products looks like. That is non-hygroscopic. And the last curve looks like a C. This is a product, usually it's high salt and sugar. So what type of products? Hot dogs maybe fit that category. Okay? That's why in the hot dog, let's say we have a summer sausage, the water activity is lower, 0.9 below. We don't worry about too much. Once the product is like a hot dog, when the water activity is higher, we worry about these foodborne pathogen contamination. Why I want to mention here? Because the sorption isomers really related to the packaging. This is a good example. The instant coffee is usually we sealed in glass containers with moisture-proof seal, thick PVC, polyvinyl chloride, we acronym called PVC packaging. It's a lot, you will see a lot. So instant coffee, you take it out, you see there is a small foil, like a foil paper, the film on the top. That's thick PVC film. Why? What's the reason? Because instant coffee is a hygroscopic product. They will reach critical moisture area before they reaching external climate conditions. That means they have a very steep isothermal sorption isomers. Okay. Now, most of the other products, they can be packaged in the polyethylene containers. And we try to prevent the moisture loss like cheese and the baked goods. That's the example why we have to do sorption isomers. To determine whether it's hygroscopic or non-hygroscopic or like high salt sugar capillary products. Here is a give you example. If I want to make a dry soup mix, so there's two components: 2% freeze-dried vegetable, 13% moisture of starch. Then you mix it. Will generate 9% of the moisture. What we have to do, you have to make it pre-tested, and then remake it and retest it. And always remember the water transfer from high moisture to and the vapor pressure to low products. And this is a formula used to calculate what is the final water activity of these products, of this dry soup mixer after you combine them. So W1 equals gram solids of ingredient 1, S1 equals linear slope of ingredient 1, and the third index indicates initial water activity of ingredient 1. The same thing as ingredient 2. So you have to do a calculation, and you have to redo it. That's called post-dried again. Okay, which means you mix them, you need to do a calculation, the relationship between water activity and the moisture, and then you post-dry it. When you mix it, you post-dry it. You can't just say, oh, this high, this low, we mix it, it's going to be safe. No, you have to post-dry it. Now here, in some of the textbook, so it really confuses you a little bit here. This is relative humidity, and we some of the curve use water activity. What's the relation between that? Is relative humidity divided by 100 equals water activity. Okay, so that's something you need to know. The y-axis is always same, the moisture. And now I want to mention again. This is water activity and the moisture. Can you see that? This is relative humidity and the moisture. So you need to know that's the same thing. Just the relative humidity divided by 100 is water activity. Those are the same thing. Okay. Okay. So we finish here. We finished talk about all these related to chemical stuff. This one is really for bacteria. This should be talked about for the microbiology class, but we want to mention about here a little bit. Based on the water activity and the pH of food products, we can categorize into 4 basic categories. We don't really care about all these 3. You never heard about the acid controlled foods because we don't really care about it from the microbiology safety standpoint. What we really care about is low acid, actually is canned food. Okay, what is their condition? Water activity more than 0.85, pH more than 4.6. This is low acid canned food. Why we care about this? Because of endospore caused by Clostridium. Typical Clostridium botulism. Okay, Clostridium botulism have 3 levels, 3 types. This is number 1, infant botulism. You're never gonna feeding a 1 year or less than 1 year old newborn baby honey. Otherwise, you will have a floppy baby because of the Clostridium botulism. Number 2, wound botulism. If you have cuts, bites, or like abrasions on the wound, on the skin surface, you may get contaminated because Clostridium, most of them come from soil. The third one is food botulism from the canned food. Okay? What's the results will cause botulism. Think about the floppy baby, what's going to have is muscle softening, no contraction. What's the result from Clostridium tetanus? Is locked jaw, is muscle highly contracted. So it's opposite. The reason is there is a neurotransmitter which is acetylcholine and the chloride. One is inhibit one, another one is inhibit the other. Is that right? You can go back to look at your microbiology slides. And that is talk about that. That is, we care about this Clostridium. So what we do, so low acid kind of food, what we do? Of course, the first thing is measure the pH. Now in West Virginia, usually used to be the Susie, Dr. Brad Kenny's research assistant. She passed away last year. She did the service for the whole state, which is all the low acid candle, the pH has to be less than 4.0. That is standard set up by the WV, West Virginia Department of Agriculture, for the low acid food is 4.0. Now in the industry, how we do it? We do is we make sure you add citric acid to low down pH to 4.6. And we use high pressure cooker to make sure it's reached 15 psi, 121 degrees Celsius. The idea is to kill endospore. Okay? These usually it's like a valve. Then you have a panel there, make sure it's good. So high pressure cooker. So just something to let you know. Low acid canned food is more important. How do you know it happens for a low acid canned food is damaged? You see that the dent there, you see it's concaved, or you see there is extracted of the liquid compounds. That's not good. Okay, those are the phenomena which is indication tells you the can has been contaminated. Okay, something else is more application for food chemistry, for food processing, because it's for the chemistry class. We're going to talk about something for the food. Okay, this is very important. We mentioned about two important things for food products: water activity and the pH. For meat products, the pH is very important because it's highly related to water holding capacity. Water means water holding capacity, which means meat products